Hello friends, in this video we're going to be entering chapter 19, which is regarding chemical thermodynamics. And before getting into the content, I'll give us a small refresher of um, some important concepts that we need to keep in mind. So first would be a state function, and this is defined as a function that is path independent. So an example of this would be temperature. If you have this pot of stew initially sitting at 25 degrees Celsius and then you heat it up to 100 degrees Celsius, well, let's say you heat it up in phases. So if you heated it up in phases, what's going to happen is you first heat it up and then you let it cool down, heat it up again and then let it cool down until you repeat that process to get 100 degrees Celsius or your desired boiling point. Well, it doesn't really matter how you do that in the terms of if we're looking for the change in temperature, we're just going to be looking for the final temperature minus the initial temperature. So that would be your 100 degrees Celsius minus the 25 degrees Celsius, and we can see that there's a 75 degrees Celsius of change. And here I illustrated it in a graph. So you can take multiple paths. First, you can heat it up completely and then let it cool down and stabilize, or you can heat it up in phases, and you can have all sorts of wacky little functions to describe the change in temperature. However, the only thing that's going to matter is your initial and your final. Think of it sort of as a slope, right? Other variables also work like this. For example, we have volume in terms of you can think of this as filling up a beaker. We have our pressure, and what we're going to be introduced to in this chapter is something known as entropy, which is also a state function. So we can say that our change in entropy, given the general formula of our final condition minus our initial, is going to be equal to our final entropy minus initial, theoretically, right? Okay. Next, something that we can look into is the types of systems. So I'll erase this delta H. First of all, there is an open system. So an open system is one that has direct contact with the surroundings, and thus the surroundings can become a variable or a factor as to how the reaction is processing. Next, we have closed systems, which would be this one, which the system under study is not completely isolated from the surroundings, but there is a level of isolation that is preventing certain surroundings to impact the actual experiment. And then finally, we have an isolated system. These types of systems are completely separated from any kinds of surroundings that may be interpreted as destructive to the case of study. And that's about all we need to know about systems. So now we can approach section 19.1, which is the actual content in chemical thermodynamics. So section 19.1 is going to introduce us to something known as process. So what processes are, it's technically the procedure in which a reaction works. And I use the word works because it has a direct correlation to the work function, which in physics would be your force times your distance, right? Okay, so something important in chemistry is that we are not generally dealing with force. So how would we define work? Well, work in chemistry, there are several interpretations, but one that we'll surely be looking at in this chapter is known as PV work, your pressure volume. And that is just something to keep in mind. And this type of work, it's going to have a direct correlation to a process, which we'll be exploring much further in section 19.5, which deals with the Gibbs free energy. So here it tells us that there are two kinds of processes, and these two right here are going to be essential subsets of these processes, things that we can infer. So now, a spontaneous process is defined as one that occurs naturally, without the assistance of its surroundings. So one example would be the melting of ice. It just occurs naturally. Given a temperature, if it is above 0 degrees Celsius, it's eventually going to start melting, right? So it's a spontaneous process because it's occurring naturally. Because what is defined as a non-spontaneous process is something that requires direct manipulation or work in order to occur. So one of these examples would be, for example, you have an egg, and then you drop it, that egg breaks. A non-spontaneous process of that egg would be to take the egg and somehow fix it and formulate it in such a way that it's into its initial condition of an egg. And that's non-spontaneous because it requires work to do it. And what we can say is that a spontaneous process goes only in a single direction, right? So in the example that I just gave you, if we have this egg, dropping it and watching the egg break, that's a spontaneous process because the egg is breaking naturally. However, a non-spontaneous process, something that needs assistance in order to occur, is to watch, to have the components of the egg and to somehow put them together. And here I have noted an isothermal process. This is a certain kind of process that we'll be looking into later in this chapter. But an isothermal, the meaning of isothermal, it just means constant temperature. So just keep in mind that a reaction of some sort is going to be occurring at constant temperature. And that is going to be very essential to what we'll be talking about. And next is these two subsets, which are the most critical, these four technically. There are things such as reversible processes and irreversible processes. So a reversible process is one whose system you can imply is at equilibrium. So that means that the reactants and the products, given you give some sort of change, they're going to be converting into one another constantly. So let's say that we have an acid-base equilibrium equation, right? So that'll be fine. And let's say that it's at equilibrium. Well, if you add more acid into the dissolution of an acid, what's going to happen? Well, what's going to happen is that the reaction is going to shift one way, right? And if we add more of a base, it's going to shift the opposite way. So this form of equilibrium is what I'm talking about. It's going to be a constant conversion of reactants to products and products to reactants. An irreversible process is not at equilibrium. So it's sort of the most realistic kind of process, right? Because it's difficult to see a process at equilibrium in nature. So these irreversible processes, they are spontaneous, right? Okay, now we can get into our example, which is the one I described earlier. So first we have the egg in its natural form, right? We drop it, it breaks into its components. That would be a spontaneous and irreversible reaction. Spontaneous because it occurs naturally, the breaking of the egg, and irreversible because there's no way that we can get these components realistically to the way that it was before in its primary condition. At equilibrium, we have this. And this is what we call a reversible reaction. So what we need to keep in mind is that these two equations are essentially opposites. And the reason why is because, again, you cannot get the eggshell plus the yolk plus its other components and then fix it to its egg and say that is a spontaneous reaction. Because it's not. It requires work to do all of this, right? And it's going to require some help from the surroundings in order to do this process. So it'd be non-spontaneous. So here we have the big ideas. Processes that are spontaneous in one direction are non-spontaneous in the opposite direction. And this makes sense. Things that occur naturally, they are one directional, so they're not going to be at equilibrium. But from this, in order to get the components that it left over in the spontaneous reaction, in order to get them back to the way they were, it would require work. And since it requires work or help from its surroundings, it would be non-spontaneous because it doesn't occur naturally. And here we have these two facts. All real processes are irreversible, and all spontaneous processes are irreversible. And this brings us to our final point. It's mainly just theoretical, but it's good to keep it in mind. So we know that all real processes are irreversible. So we know that there are no real processes that are reversible. And the reason as to why this is because a reversible process has some serious limitations. And this is the case that the system and the surroundings, they both have to return to their original states with no other changes occurring. And that's incredibly unreal. It just simply doesn't happen. So it's just more like of an idea or a representation of real processes where the system's boundaries aren't defined yet, and they need to be defined. So that's when we use reversible processes. It's simply just an idea or a representation of something, right? It's kind of like, well, yeah, it's just your theory, right? And given these conditions, this quantity of work, it has to occur in an infinitely small time so that no heat is lost or gained in the system. Because if any heat is lost or gained, then the reaction wasn't truly at equilibrium. Because that means that something either evaporated or there was some kind of dissipative force, and therefore that would not be a reversible process. So therefore, the work done has to be as its complete maximum, as high as it can be, so that the form of heat lost or gained is at its absolute minimum. And that is why, for a reversible process, the work done is going to be a maximum, which is just something that can help us with our calculations later on. And again, all of this is going to come down to the concept of energy, which is something that we'll be exploring in the next section with our introduction to entropy. And that just about sums up section 1 of chemical thermodynamics. So I hope you enjoyed this video. I hope you found this helpful, and if not, you can let me know, and you can ask questions anytime. I'll do my best to answer them. Thank you for watching.